Hello, general physics students. I am just going to go through our notes for today. So today it is going to be over the last section in chapter 4. The main topic of its everyday forces, but focusing on friction. We've already talked a little bit about weight or the force of gravity, or F of G, which is really just your F equals ma stuff, or mass times acceleration due to gravity. Sometimes you'll see it as AG or just G. So it's the first thing that it reminds you of. And then talking about normal force, which we covered in the last notes, or F of N. So we'll come back to that. Force of friction are on your book, pages 136 to 142. 143 talks about fundamental forces. So we're mainly in this note's going to talk about friction. All right, so I'll just put in present mode, I guess. First time going through this with a PowerPoint, so I'll see how it goes. Okay, oops, yeah. All right, so previously learned types of forces are gravitational force, or F of G, normal force, F of N, applied force, F of A, that we've talked about before. Remember that gravitational and normal force are opposite directions, and I have some review slides at the end if you're not remembering those, where this is kind of like a downward force, pull of gravity, and then upward, kind of holding something up, or opposite of F of G, and then applied force is whatever action is being applied to whether it overcomes the friction or not, because frictional force is the opposite of that. So we're going to learn about the different types. So frictional force is represented by F of F, so frictional force. It is parallel to the surface an object is in contact with, and it opposes the direction of motion of the applied force. So it's the opposite of F of A. It plays a role in calculation of net force. So the net force, which this symbol here, whoops, sorry, not used to this. I don't know how the pointer works, but it's a laser pointer. That's pretty cool. So anyway, the sum of the forces, this is sigma, which means the sum or total of them. And you take the applied force plus, I usually write it as, let's see if I can do that. I don't know if it lets me type on there, but plus the negative of the frictional force. Okay, so applied force is opposite of that, so you're adding the opposite value. I don't know if you can do that. Okay. All right, so I don't know if there's any questions about that. And then some specific type of frictional forces are static friction. It's sometimes represented as F of S, the force that must be overcome to get a stationary object to start moving. So this is when things are not moving, and it's the frictional force. You have to be able to apply more force to overcome or be able to get it to move. If it's not moving, it's a little bit more difficult to get it to move if it's not moving. So if you have a couch and it's not moving, it's going to take more force, applied force, to get it to move as compared to with the kinetic friction we'll talk about in a second. It's calculated as the maximum force an object can sustain just before it starts moving. So we'll kind of look at these with a friction lab that I'll try to get data on, maybe do a video of, like I did with different surfaces, to see what kind of force on different surfaces and how that is different. Kinetic friction is F of K. It's the friction between two objects moving past one another. So anything with movement, it's the type of friction that applies there. So if you already have a couch and it's already moving, it's a little easier to keep it moving than it was when it was still. Okay. I know that honors really struggled with the symbols and understand what those mean. So we'll get in more detail here as we go. Okay. This equation looks a little weird. I don't know why it's showing that there, but maybe I have to hit play. I don't know. That will probably play through. Okay. Sorry, just messing around there. All right, so the force of friction is really a macroscopic effect caused by a complex combination of forces at a microscopic level. It's really the interactions between protons and electrons at the atomic level and you can really see it on the macro scale or a bigger level. It's a relationship between normal force and frictional force that affect friction. So like simpler example, if it's a lot easier to slide a light textbook versus a heavier textbook across the desk. It also, friction depends on, as far as how much force is there as far as friction, on composition of the material and qualities of the surfaces it's in contact with. Okay, so coefficient of friction, mu is a symbol here. It looks kind of like the micro symbol. It's a measure of the amount of friction that exists between two objects. It's a measure of proportionality or ratio, signified by the symbol mu, or that symbol there. And so the way it describes in the book on page 138 has a really good description of it. It's a quantity that expresses dependence of frictional forces on particular surface. So it's the ratio of those forces, and that's what proportionality means. It's the ratio of something, the relationship. So I don't remember if this is kind of the breakdown of it, but maybe I'll go back. Let me hit exit, and I will go to that page that I have scanned in for you. Sorry, it's kind of tilted. It might be better in the book copy. So it talks about coefficient of friction here. So here's kind of showing the ratio setup. The coefficient of kinetic friction, so its coefficient is the mu, and k for kinetic, so movement, is shown by the force of kinetic friction as compared to the normal force. And the coefficient of static friction is the frictional static friction, the force of that to the normal force. Okay, and you can see we come up with this equation right here. The f of f is equal to the mu times the f of n. So that just means the magnitude of the frictional force is equal to the coefficient of friction times the normal force, whether that be kinetic or static type of friction as far as that coefficient value. And so you'll see when you do your book problems, which I'll explain, these are some experimental values of static. So the mu s and the mu k, so this is static when things aren't moving. These are things when they're moving as far as the frictional force approximate values. So we have steel on steel, we have rubber on wet concrete, glass on glass, ice on ice, metal on metal. So there's all these different things here to kind of give you ideas of the coefficient of friction, or that ratio of your frictional force compared to your normal force. All right, so I'm going to go back to these notes here. Present mode. So those equations are really important. It does show you examples in the book on page 139 above the book problems to explain how to use that equation. So this is just a rearrangement of those proportions or ratios. So like you see, it's the frictional force as compared to the normal force. And like I've said before, it's a lot more difficult to get things to move when it's not moving, as far as applied force to get things to move, as compared to if it's already moving, it's a little easier to get it continue to move. So static friction then is typically greater than kinetic. So remember, static is when things aren't moving, that frictional force is present there, and kinetics when things are moving. So you need to kind of pay attention on what you need to use. It's pretty much the same equation like I talked about. The f of f equals mu times the normal force. So this is just showing a relationship to your static friction is equal to the coefficient of the static friction, that value that you're either going to find or you are given, times the normal force. Okay, and we'll have to go in more detail review about normal force on how we found that. I'll do that after we go through some here. Okay, so here's a static friction problem. So as far as normal force, I guess I should talk about that. The F of G, remember, is equal to mg or ma, F equals ma, which is how we found gravitational force. Fg equals mg. So we took our mass times our gravity, acceleration due to gravity, to get our gravitational force, which is actually going to be equivalent to your normal force as long as it's horizontal. So you can see on this one, it's resting on a horizontal patch. So as long as it doesn't have an angle for right now, we're going to learn the ones when they don't have an angle, how to solve for either the coefficient of friction, which is, remember, the mu, or to solve for the frictional force, whichever that might be, if it's static or kinetic. So in this problem, it says a sled is resting on a horizontal patch of snow, and the coefficient of static friction is the coefficient of static friction, which is the symbol here, is equal to 0.350. The sled and its rider have a total mass of 38 kilograms. What is this magnitude of the maximum horizontal force that can be applied before it begins to move? So with this problem here, you have your needing to solve for normal force, of course, to be able to solve for frictional force. So normal force, remember, is m times g. So you have 38 kilograms times 9.8. Maybe this would have been better to do on the next time, maybe on a blank document so we can see it. So normal force is 372.4 newtons. Okay, that's taking the 38 times, which is kilograms times the 9.8. That's our normal force. And then to get the F of S, you're going to take the 0.350 times that normal force to get the F of S. It's because it's the coefficient times that. So you end up with 130.34 newtons. So maybe that is something that, get out of this here, maybe. Let's see here. I guess I could hit pause. Okay, so I ended up showing my work on here, like I was just talking about, how your F of G equals mg. There's plug it in, your mass times your acceleration to gravity, so you get this value. And then we know these are equal because they're opposite reaction types. So there's that value. And then our equation for frictional force or static friction. To solve for that, we got our coefficient of friction, which was given, times the normal force. So you end up with 130.34 newtons for your static friction, which you can see is on this slide here. Okay. Hopefully you followed along with that. All right, so same type of thing with kinetic friction. It's always, we talked about always being less than static frictional force. It's represented by F with sub K. 3 things to keep in mind as far as kinetic friction or movement, friction that you're dealing with when things are in movement. Number 1, area of surfaces in contact doesn't matter if they're already moving. Speed doesn't matter. And the kinetic friction is proportional or has a ratio, like we talked about, to the normal force, which ends up meaning, if you look at that page 138, that's provided to you, see that relationship given to you, the mu k equals fk divided by f of n, which if you rearrange it and solve for f of k, it's normally how you see this, is that frictional force equal to, again, the coefficient of friction times your normal force. So same type of thing as far as solving for that. It's just a different type of coefficient of friction. Normal force will stay the same if it's horizontally moving. Okay, here's a kinetic friction problem. A sled is traveling at 4 meters per second along a horizontal stretch of snow. The coefficient of kinetic friction is 0.05000. How far does a sled go before stopping? There is no up or down motion, so the normal force is equal to m times g, and therefore your frictional kinetic friction is equal to, you just take your coefficient times mass times gravity, because that's all that is. That's what normal force is. So that's another way of looking at it. Instead of just having f of n here, you can just write it as m times g. Friction is the only thing acting, so it is the net force, and we can plug it into Newton's second law, F equals ma, and rearrange to solve for acceleration. Okay. And then here's a broken-down equation of acceleration of what we could use. What happens is, if you see this equation here, it's just showing how it's broken down. If we change it there, you have the, that's just really just rearranging. So taking this here, remember G is like your A, so they're just rearranging to get A by itself on one side. It's all they're doing there. So it's a native coefficient of kinetic friction times the mass times gravity divided by m. You can see the m's cancel out. So then acceleration, one way you can solve for acceleration is taking the negative of the coefficient of kinetic friction times the gravity. So we can take, let me pause this real quick. Oops, sorry. Exit this. And then it also says how we can use our equation we've used previously with our projectile motion vector type stuff. The velocity squared is equal to the initial velocity squared plus 2ax to solve for the distance as well. Okay, so based on this here, I have the equation that I've already had. The kinetic frictional force is equal to the coefficient of the kinetic force times the normal force. Okay, and we rearranged it later on, and we'll get to this, how we use these two equations that it mentioned on the slides. I'm identifying my variables. The final velocity that it's given is 4. The initial, I'm assuming, is 0 because it started at not moving. And then the coefficient of kinetic friction is 0.05000. The mass ends up canceling out like it showed on this slide here, how it canceled out, and you're left with this for acceleration is equal to that. So we don't have to worry about that. And so you can use that to find the acceleration first, which is shown over here. And then we can use that finally to find the distance. I think it said, how did it say it? How far does the sled go before stopping, before the frictional force takes over enough? So you have your coefficient of kinetic friction times your gravity, and you get 0.49 meters per second squared. And then we can plug this in for x right here. Sorry, not x, my fault, for acceleration. We're going to solve for x. So you got 4 squared here is equal to 0 squared plus 2 times the acceleration we just found times x, which is what we're trying to solve for. Maybe I should put that in red too so we know where we're at here. So we're trying to solve for that. So as long as I did everything correctly, we squared the 4, that got 16. Right here, that goes away. 2 times that was 0.98. And then we divide both sides, and you're left with, double check this, make sure I plug this in correctly, 16.33 meters is what you get for how long it takes till it stops. I will make sure to add maybe a few slides in there about these showing the work so you can see that as well on the slides. Okay. Another thing here that we can talk about, we'll actually be practicing more in detail with frictional force, like I told you, with when they're at an angle and how to overcome friction. So we'll go in more detail later with some practice as we go through things. One thing that I do want to introduce and make sure that we'll get practice on it, some initial practice on it. We'll see how in depth we go. I won't be as in depth as honors does, but I want to make sure I introduce it because it's something that you might see in physics when you get to the college level. So our 4 types, you can see our 4 types that we normally talk about here. We got normal force, or F of n. We have gravitational force. We have the applied force, usually shown as Fa, and the F of F, or frictional force. You can see that these are opposites, right? And normally they're equal, not always, just depends on the situation. And then applied and frictional are usually opposite type things, where applied's going this way and frictionals going the opposite or opposing the motion. These will actually all show all the force vectors acting upon a person or object, so you'll get some practice with that and trying to identify some different scenarios and trying to draw what's applying there as far as that. So we will be practicing that later in the week, along with more detail with friction. All right, so the homework slide here is from the Holt textbook. I did add this page number as well as 138. The coefficients of friction problems. It's 1, 2, and 3. Number 2 and 3 have multiple parts. When you get to number 3, take note, it says use the values in table 2, which is on page 138 that I pointed out earlier, how it gives the coefficient of static and kinetic friction on those. And you actually have to solve for both using the values that you have there. Just remember that you take for F equals ma. If you just remember that, mass times acceleration due to gravity is what you're going to use for F of g, which is equivalent to your normal force. So you're going to use that along with, you have a mass given, and then you use the acceleration due to gravity as far as that, and that will get you your normal force when you multiply those. And then you are solving for, you're trying to solve for the frictional, static friction and the kinetic friction. So you're using the coefficients that are given on the other slide, or their, table, to plug those in and solve for the F of S and F of K. On number 2, actually on the first 1 and 2, you're solving for a coefficient of either kinetic or static friction. So going through those as well. So just remember static, the values you use would be when things are at rest. If something's moving, that's when you use the kinetic values that are given in the problem. So if there's any questions on the book problems, let me know, but it's really important to attempt those and show your work, whether that's in your online science journal, or maybe you have your journal at home. I don't have all of them because not everybody left theirs. Or a piece of paper if you want to show your work. Because for me, it's a little difficult, not being at a whiteboard and being able to show my work and do the problems a lot quicker as far as having them all typed up. I guess I could have wrote it down. It's a little neater than I would write on the board though. So we'll just take it as it comes. I don't know, maybe next time I'll do something with, I did bring a whiteboard home, so we'll see on how these go as far as what's needed as we go through different things with notes. But that can be in your online science journal again or on paper. Just got to attach it to this assignment on the classroom. And then as long as you add it on the classroom on this assignment, then I will be able to open it. But don't forget to submit through my form so I know that you turned it in. So that's how I grade them, is when you guys submit through my form. I'll come back to talk about that later. So that's assigned homework. I think I put it for Thursday. I don't know how much time you need. It should be able to get it done. Do your notes in your online journal, like the stuff we're going through the video, or whatever. You can take down like the quick main idea notes in your online science journal, so you have those to refer to as we do things. And then your problems can go in there as well if you want. Just make sure you keep your table of contents updated. Here's a good overview review slide that has all the variables. I know with honors, they really struggled with, and I'm assuming you guys would too, because I know we have before with variables. We have a lot of variables, like when we did our kinematics, it can get very confusing. So I have all these on here, the main like symbols up here, and then kind of broken down. You got force, which you guys all know, you've done really well with, F equals ma or F equals mg, or you might have seen it as Fg equals mg. So force is equal to mass times acceleration, Newton's second law. Net force, this symbol here means sum, okay, the total, okay. On one of those earlier slides, we had the sum of the forces equal to the applied plus, well, it showed it as the minus frictional force, or you say adding a negative or opposite direction as far as the value. And then normal force is an upward direction. It kind of pushes things. It's that contact force that holds things up or pushes it up. Gravitational force pulls things down. So those are opposites. Applied force is what you're applying, and it goes one direction, and friction force is the opposite direction of the applied. So those are kind of opposites as well. And then we have specific types of static. Friction, remember, is when things are, it's the friction when things are at rest. And the kinetics, the frictional force is present when things are moving. And then coefficient of friction, which you use to solve for the F of S and F of K. It's that ratio of taking these as compared to the normal force. Okay, so hopefully that helps you a lot. I think it did help the honors kids a lot. It's just breaking down and making sure you know what each variable means. And this is an index card. I don't know if I can click so that this, I don't know what that does. Okay, there we go. See? It kind of covering the index card. But anyway, here's just kind of random things. We're not going to get to this yet, but that is when we'll go talk about gravitational force in our next unit. We'll be learning that equation there. These might be useful, maybe, if you want to use it to find. That's another way you can find normal force. Here's our equation that we solved before with F of A, F of F, sorry, and then here's an equation with A. We haven't gone into detail right now about anything with cosine or sine. And these are just different equations represented, talking about normal and gravitational being opposite, coefficient of friction. As far as solving for that ratio is what that means. Them set up to each other or divided. Okay, and here's some 9.8. Okay, that's just the mass radius of the Earth. This is just a kind of a note card to kind of explain basics on some of the stuff we covered. So hopefully that was helpful. I'm trying to think. That went pretty well. I mean, you're really just doing the problems, remember? So hopefully you went through, and as you were listening to the video or looking through the PowerPoint, you hopefully took notes in your online science journal or a notebook paper to attach, submit through the form. But my main concern is obviously, doing these problems and making sure you guys are understanding it okay as far as focusing on the coefficients of friction. So Not too much detail yet, and then we'll go into free bodygrams as well. And so it's not posted till tomorrow morning. I'll have to add this video on there, but on Classroom, I'll have to add this on there as well. I'll make sure I copy those into, when I'm done with the video, into the PowerPoint. So I do have the online science journal right now under the general info. I just stuck it up there right next to the lab notebook. I wasn't sure where to place that for now. And so these will be attached tomorrow. This is the PowerPoints. Information, the video will be on there too. I don't know if it makes more sense to be separate or not, but I'll just put them together. And then these are the assigned book problems. It is on the last, or not the last slide, one of the last slides there. I'd have to look to see what slide that is. Actually, slide 11 it looks like. And then I assigned it as a separate book, so you know what you're supposed to complete for that. So anyway, as far as this, hopefully you don't have any questions. You can take notes in the online science journal. If you guys as a class want to move this somewhere else, I just figured it'd be good so you can know where that's at all the time. And then there's your old review online learning. So a big one that I would do if you haven't done anything would be the vocabulary review would be a big one. I mean, these are all good as far as talk about force. But the vocab I definitely would do. Maybe these review questions would be a good one as well. Graphing review is a good review. The Kahoot, maybe that's a good one to do. I just try to pick a variety of force things too. The OLC, I tried to mark those as which ones were online classroom that we've done so far. So I did assign this one today. So if you didn't get a chance to do this one, go do that to review your knowledge of scientific notation. And I will get caught up on stuff. I have most missing work caught up for your class, I believe. For general physics, I think there's a few more kids that turned in stuff. I did not put a grade or anything yet with the egg drop project, but I probably should at some point. I did have more turn it in, so I thank you. Hopefully more people participate with this new learning as far as things as well. If you have any questions from the notes or anything else that's on here, I'm trying to make it organized for you. So we're just going to finish out the unit. You know, the unit was actually what we did before break was down here, and so it's not confusing. I'm just making sure I'm adding it as an online. These are all the review stuff, so I wanted it as a separate thing. And each time we'll have a new unit, I'll just say new online learning classroom is what that stands for, and then I'll say what subject it is. So it might get kind of lengthy, but all right, I'm going to go ahead and push pause or stop the video. So contact me through email if you have any questions. Hopefully this was helpful.